Hi, this is Zach Kaplan. I don't think I need to say welcome to PST Art Open House again, but welcome. There are some new people coming through every time. As I said at the end of our last performance, we've now left Earth. We're going very far out into the solar system and beyond. This is a great honor to collaborate with Berggruen Institute on this part of the evening. I think I've been talking to Claire for over a year now about how to bring PST and Berggruen Institute in conversation to one another, because right now PST art is all about art and science collide, and going into the future we'll see other art and science conversations percolate across LA, and this is just one example of things that will continue ongoing here and beyond. So I want to thank the Berggruen Institute for participating, and I want to welcome Dr. Claire Webb to introduce Proxima Kósmos.
Your heartbeat is a clock in the universe. Place your hands on your chest. Take in a long, deep breath. Hold it and count to 4. Feel your heart pump life through your body. Breathe out, counting to 6. Feel the blood flowing back to your heart, thirsty, seeking. Each breath of life is a mere sliver of a blip, of a fraction of cosmic time. Keep breathing. And as you do, imagine each heartbeat transporting you hundreds of millions of years into the past. You morph. You shrink. You turn green. Your respiration transforms into photosynthesis. Your lungs harden into something like plant matter, more rigid, more structured. You absorb the energy of an earlier, dimmer, lemon-hued sun. You weave about in a warm, ancient ocean with innumerable companions, Earth's primordial life forms, cyanobacteria. Some 2.5 billion years ago, our planet was a different world. Carbon dioxide clotted the atmosphere, trapping in heat. On a world much warmer than it is today, life that lived without oxygen dominated Earth's swirling, rose-pink oceans. But then, cyanobacteria made an evolutionary leap. They harnessed a green pigment called chlorophyll. This new breed of bacteria began to convert sunlight into energy. Those microscopic, single-celled organisms transformed the planet. They made an oxygen-rich atmosphere that life, as we know it, has relied on for billions of years. Cyanobacteria breathed life into our planet. They dyed Earth's rosy oceans cerulean blue. They remade our world, and our world made you. The arrow of time that links those ancient organisms to you today is just one possible evolutionary path of our planet. Present understanding of life is limited to a single sample, Earth, a planet of rock and water, orbiting a yellow dwarf sun on a spindly arm of the Milky Way galaxy. Life here is special. It's perhaps even unique. But what if events in our planet's histories had zigged, not zagged? What if cyanobacteria had never met chlorophyll? What if 66 million years ago, the asteroid that wiped out the dinosaurs had missed Earth? What if, tens of thousands of years ago, we hadn't bonded with wolves on grim glacial plains? Whether they be on an astronomical scale or a microscopic one, considering any one of these changes in our planet's history could have completely altered humans' journey. What ifs open us up to the wondrous and seemingly limitless ways in which life on Earth might have unfolded. Trillions upon trillions of paths not taken. So many unbloomed nows. What might have been here could be beyond. But where to begin the search for extraterrestrial life? Since the 1960s, we've sent humans to the moon to collect lunar soil. We've landed rovers on Mars, sent spacecrafts around Venus, and photographed moons at the edges of our solar system. Today, we use new technologies and telescopes to study exoplanets far, far away. And yet the existence of life beyond this planet remains a deep mystery. To better search for what's out there, we can start by building alien life right here. For over a year, I've been collaborating with planetary scientists, astrobiologists, artists, philosophers, and other scientists to explore where extraterrestrial life might exist and where it might reveal itself. Working with renowned scientists at MIT, NASA, and other places, we've dreamed up planets where life is strange, yet familiar. The worlds we've made are grounded in advanced scientific modeling, planetary simulations, and evolutionary projections. These worlds combine fields of astrobiology, planetary science, and artificial intelligence to construct life as it might be otherwise. Each planet is a distinct laboratory for the origination and the evolution of alien life forms. We fabricated different ecosystems, caves, clouds, and oceans. We clocked various time periods, 2 billion years, 12, 20. Once we did that, each location was ripe for life to form. It was time to test the scientists' hypotheses. So we pressed go on the simulations. And like aliens observing the planets, we witnessed life taking shape. Welcome to Proxima Kósmos, a solar system that is similar but not identical to our own, home to 9 speculative worlds. The first planet we'll be exploring is Phaenotera. Phaeno, from the Greek, means to shine or to be resplendent. Phaenotera's shiny bubblegum atmosphere may look inviting, but it's the result of millions of years of built-up greenhouse gases, acidic oceans, and sulfuric clouds that would melt your face off. As we get closer to the surface, another definition of Phaeno becomes more apt: to reveal or to become evident. If we look close enough, this seemingly inhospitable planet reveals the existence of something that shouldn't be there. Imagined and built by MIT planetary scientists Dr. Sarah Seeger and Dr. Iaroslav Iakubivskyi, Phaenotera compels us to rethink the basic chemistry of life. Please welcome Dr. Iaroslav Iakubivskyi.
Now that Claire has brought you to the planet, I will be your guide as we descend into the dense acid clouds of Phynoterra. But before we go further, ask yourself, what if alien life has been hiding in plain sight? Phynoterra may have started like Earth, a familiar atmosphere, oceans, and rivers, but over time its fate diverged. Volcanoes erupted, thicker clouds formed, and tremendous heat was trapped in its atmosphere. The greenhouse effect intensified, the oceans boiled away, and when the water was gone, sulfuric acid remained. Now, its sky glows fuchsia, its mountains rise tall, much taller than we are used to here on Earth. The atmosphere is thick, crushing, and hyperreactive, capable of breaking down most known biomolecules. And yet, something, like life, may call it home. Phynoterra was built from a question, one sparked by discovery in our own solar system. Could life evolve in such an extreme environment? In 2020, a team led by exoplanetary astronomer Sarah Seeger detected something unexpected in the clouds of Venus: phosphine gas. On Earth, phosphine gas is toxic, reactive, and rare, and it is only produced by bacteria or factory emission. Its presence on Venus, a planet with suffocating atmosphere where surface temperatures are hot enough to melt lead, poses a profound question. Could something there be alive? If phosphine exists on Venus in any meaningful, detectable amount, some process we don't understand, must be replenishing it. And that raises an even bigger question. Is this process merely chemical? Or could it produce biology? If phosphine is truly biotic, then life may not need the conditions we once believed were essential. It may not need water at all. To test the possibility of life in an acid-dominated world, our team at MIT, including myself and other researchers in the Department of Earth, Atmospheric, and Planetary Sciences, needed a planet like Venus, but one we can control. Phynoterra became that test case. On Earth, sulfuric acid is destructive. It burns through your skin, dissolves metals, and devours organic matter. But what if, on Phynoterra, sulfuric acid sparked life? Our team built a cloud chamber to mimic the basic conditions on Phynoterra's atmosphere. We submerge life fundamental building blocks, amino acids, nucleic acids, lipid-like structures into sulfuric acid at varying concentrations, just as they might exist in the fictional planet's haze and surface pools. Expectation? The molecules should dissolve, breaking down beyond recognition. Reality? 19 out of 20 biogenic amino acids survived. And although some amino acids underwent chemical modifications, their fundamental structure remained intact. Some even exhibited increased stability under these conditions, suggesting the potential for acid-based biochemistry. This shattered long-held assumption about the limits of biochemistry. If life molecules can survive here, what else is possible? To push our understanding further, I traveled to Ijen Lake in Indonesia, one of the most acidic bodies of water and the largest sulfuric acid lake on Earth. For science, I got as close to the lake as humanly possible. The scent of sulfur was overwhelming. Each breath felt like inhaling the ghost of a matchstick. The water in Ijen Lake has a pH even lower than a battery acid, meaning it is far too harsh for most known life. Yet, microbial communities thrive in these waters, forming biofilms, protective layers that allow life to persist in conditions that would kill them. If life can adapt to this, extreme on Earth, why not to similar conditions in the clouds of Venus? Why not on Phynoterra? Let me show you something. Peer into the clouds. Do you see them? Floating in acidic haze, these tiny, Bubble-like organisms battle the turbulence. Their membranes use acid-resistant outer layer, keeping their internal chemistry stable in the atmosphere that should dissolve them. Here is one, elongated, covered in fine hair-like projections. This allows to stay suspended in the clouds, adjusting to changing currents. And this, a jelly-like structure, with filaments radiating outward, it maximizing surface area, pulling resources from the atmosphere itself. They aren't just floating, they're moving, gathering, clustering. Some may even be exchanging chemical signals, a primitive form of collective intelligence. Now, let's descend. Look at the pools below. These organisms float. They also cling to the rocky edges, forming strange protective layers. These microbes have adapted to a more anchored existence. See the circular one? They have distinct layer membranes, allowing them to regulate acid intake and store sulfur as an energy reserve. Other microbes are elongated, with rigid exteriors. Their internal compartments are designed to control ion flow, keeping them stable in an environment that should tear them apart. Instead of sunlight, these microbes extract energy from the chemistry of the planet. Despite all odds, Phaeoterra's pools are living, breathing, metabolic biosphere. These microbes shouldn't exist, and yet, here they are. Phaeoterra could be the future of astrobiology. Life on Venus is no longer a question of speculation. In the next decade, the Morningstar missions to Venus will send the first direct probes into the planet's clouds in over 40 years. Their goal? To analyze the atmosphere, to test for exotic chemistry, and even life. If, or when, we found something, the chemistry of life will change. Thank you.
What if life operated in an entirely different realm of physics? At the farthest fringes of the Proxima Kósmos system, we find Nyctoterra, an entity made of an invisible, elusive substance, dark matter. What is dark matter? Although it makes up most of the universe, the truth is we just don't know. We can't see it, we can't hear it, but we know it's there because we can measure its gravitational influence on stars and galaxies. Dr. Jaco de Swart from MIT and Ranger Liu from the University of Washington have created a planet that exists not only at the edge of our solar system, Proxima Kósmos, but at the farthest reaches of human speculation. As strange as it may sound, lively dark matter is based on theories from some of the leading scientists of our time. Please welcome Dr. Jaco de Swart.
Darkness. Probing darkness. Trying to see the invisible. It is the most fundamental part of the astronomical sciences. In astronomy, we strive to reveal parts of the universe hidden from our normal senses, to shine light on darkness. We make use of theories and telescopes to observe stars, galaxies, black holes, and even the origins of the universe. Yet, our instruments have limits, and there are still some deep cosmic unknowns that keep us in the dark. And Nyctoterra illuminates them. Nyctoterra is a dark matter world, formed from low-mass atomic dark matter. It lacks a dense core and instead remains in a constant state of cloud-like being. For our speculative planet of Nyctothera, meaning night in Greek, we decided to mash together two of science's greatest mysteries: the detection of life beyond Earth, and one of the most urgent Nobel Prize-worthy open questions in physics: the problem of dark matter. It's one of the key hypotheses in modern cosmology that 85% of all the mass in the universe is invisible. And we call that stuff dark matter. And the idea of dark matter came from a very simple observation about half a century ago. Astronomers noticed that the galaxies that they were studying were moving way too fast. They were spinning much faster than the gravity of the visible mass could hold together. So fast, in fact, that, according to theory, these galaxies should have blown apart long ago. Astronomers could only conclude that there must be extra gravity holding these galaxies together. A vast, hidden force caused by an unseen mass. But now, what could this invisible matter be? By far the most popular proposal was that the dark matter was a new type of elementary particle, like an electron, but neutral, much smaller, and incredibly abundant. And they call this object a weakly interacting massive particle, a WIMP. Yet, after 4 decades of searching with massive detectors in the air and underground, there is still no sign of this WIMP. Dark matter remains elusive. And that's why many new ideas have popped up. Perhaps dark matter might be mini black holes, maybe more exotic particles. And there are even theories that say that we have misunderstood how gravity works. And then some physicists are considering another extreme possibility. And that's one that really keeps me up at night. What if the dark matter is not just a single particle, but an entirely hidden physics? A dark sector where dark particles, dark forces, and dark structures could exist, forming a parallel but separate cosmos. The dark sector would not interact with ordinary matter, except through gravity. It could be an entire cosmic architecture with dark atoms and dark molecules, invisible but present. And some researchers have even suggested that, under the right conditions, dark matter could form stable exoplanets. And if that's the case, could dark matter also form life? Enter Nyctothera. Imagine creatures unlike anything we know. Not solid, but gas-like. Polymorphic entities existing in a delicate balance of gravitational fields. Their bodies stretch and contract with the shifting gravity of their world. Their forms are never entirely fixed. Meet the Nyctotherians. They have no eyes, no ears, and light goes right through them. And sound does not exist there. Instead, the Nyctotherians perceive the universe solely through gravity, sensing the tiny ripples of space-time, the shifts in force, and the gravitational distortions around them. Nyctotherian life is not based on light, sound, or touch, but on gravity. To them, our world, our human way of perceiving is incomprehensible. And to us, the Nyctoterans remain undetectable. So, as humans have searched for life beyond Earth, we've listened to radio signals, scanned for habitable zones, and searched for the signatures of water, oxygen, and carbon. But what if? What if life exists in forms that we are fundamentally incapable of perceiving? What if the universe is full of intelligence, hidden not by distance, but by the laws of physics? If Nyctotera exists, we do not know. But perhaps we are already sensing its pull. The next great discovery in astronomy may not be about what is hidden to our senses, but about reimagining what it means for humans to sense it all. Thank you very much.
What if biology and technology co-evolved so that life's complexity complexified itself? We've now arrived at Magikos, the third and final planet we'll be exploring on today's journey. From a distance, the casual space traveler might mistake Magikos for Earth. Dense clusters of bright lights dot the landscape, illuminating connections across the planet's surface. Here, however, biology and technology have fused at a planetary scale. Life here is so complex, networked at such a large scale, we could say that the planet itself is a life form. PhD candidate Estelle Janin and Dr. Sarah Walker from Arizona State University study the relationship between life and complexity. The world they've dreamt up as Magikos configures Earth in a far future, one where intelligence is no longer restricted to individuals, but cascades across an entire world. Magikos presages what Earth could become, a collective planetary intelligence, what scientists like Estelle call a mature technosphere. Please welcome Estelle Janin.
Behold the surface of Magikos. Everything around you unfolds in woven, intricate structures, a layered tapestry of networks and interconnected objects, shaping the world in heartfelt complexity. You can almost feel the planet pulse. Matter is shifting, moving, building. The entire planet is thinking. Magikos has grown itself layer by layer, accumulating existence in a unique way and storing echoes of its past in its very structure. This world remembers itself, selects upon itself, and in doing so, it evolves ever greater complexity. Astrobiologist Sarah Walker and I, through a new framework called assembly theory, study the relationship between life and complexity. Think of the universe as constantly exploring the space of possibilities. Not everything that can exist does exist, and choices have to be made. If it wants to build upwards in complexity, the universe needs to commit to specific trajectories. It must choose depth over breadth. But the more complex an object is, the more steps it takes to construct it. If it wants this object to persist, the universe must be able to make many copies of it. Therefore, it needs to remember how to build this object. Committing to build some objects rather than others, and retaining the memory of how to build increasingly complex objects is what we call selection. And selection is exactly what life does. It produces complex objects in abundance. In other words, life is the best way the universe has found to explore and discover itself. You and everything around you is the product of selection and evolution. And Magicos is the perfect example of an object so complex, so deep in time, that it is ripe for a new phase transition. There's no single intelligence here, no centralized ruler, no ensemble of artificial machines controlling life. Instead, the planet itself is alive. This has radical implications. As I said, producing complex objects in abundance is what life does best. Molecules replicate, cells divide, organisms reproduce. Now, an entire world is about to do the same. One intelligent planet is ready to become two. The making of an intelligent planet is now robustly encoded in the universe, such that baby Magicos can be born, and itself start growing, adapting, and evolving. Intelligence at the planetary scale has reproduced. In our lab, we are not only theorizing planetary intelligence, we are testing it. Using an algorithmic program called Assembly Calculator, coupled with planetary simulation models, we study how molecular objects assemble themselves into increasingly complex structures. This allows us to investigate the boundaries of what makes a system alive. We explore how memory is encoded in matter and whether self-replicating planetary systems are an inevitable result of evolution at scale. Applying assembly theory to an imagined exoplanet, Magicos, means that we have to understand how the complexity generated at a planetary scale by a biosphere translates into our observational window for these remote worlds, their atmospheres. By analyzing the chemical space of planetary atmospheres through our telescopes and generative models, we hope to answer one of the deepest questions in astrobiology. What are the universal signatures of life and intelligence, regardless of what form they take? So let me ask you, if we had never encountered Earth before and looked at our own planet from a distance, how would we recognize intelligence? Would we assume life was confined to individual organisms with signatures that would exactly resemble those of our own planet? Or would we see the entire biosphere as one system, shaping itself, responding, adapting, the result of so many billions of years of evolution that it would undoubtedly look incredibly different elsewhere? Indeed, if we are to ever detect alien life, we must be able to identify universal signatures of selection and evolution and make the strange look familiar. This is the motive that drives Magicos. It asks us to reconceptualize life and intelligence, not as properties limited to individual minds, but as complexities that emerge and grow across scales, systems, and agents. Complexity is not just a product of biology. It is a consequence of the universe exploring and building itself. Given the right conditions, intelligence will emerge and it will spread. if Magicos is alive, then it is not the only one. There may be other planets that have crossed the same threshold, and it may be a template for intelligent life detection. Magicos and baby Magicos force us to rethink life, not just as something that happens on planets, but as something that planets become. They also challenge our ideas about evolution and the trajectory of our own planet. Magicos and baby Magicos ask us to imagine a future where intelligence is not confined to human minds, where knowledge is not just stored in books, but where entire worlds think. As humans, we often see ourselves as the architects of intelligence. But what if we are simply one phase in our planet's own evolution? Could Earth itself be standing on the edge of a beautiful transformation? A world that remembers, a world that learns, a world that one day reaches beyond itself. Thank you.
Tonight, we've shown you 3 very different worlds. We've followed what-ifs along alien pathways. We tweaked the levers of life on Earth to conjure life beyond. Remember the microscopic organisms on Phaenoterra, the dark matter entities of Nyctoterra, the planetary intelligence of Magicos. These worlds are not just fiction. They're experiments in the near future. They're worlds that we hope inspire astronomers, exoplanetary researchers, and astrobiologists to ask, what if, about the plenitude of planets coming into view today. The existence of extraterrestrial life in the universe isn't just a scientific question. It's a human one for all of us. Right now, we have just one example of life, Earth. We could chalk it up to a weird blip, a freak occurrence. But let's say we find microorganisms floating around in the atmosphere of a distant planet, or in the goo of a moon, like Jupiter or Saturn. The consequences of these microbes, like the cyanobacteria that made our lives possible, would be tiny but mighty. A single detection would mean that life is probably commonplace. With 2 examples, we'll have unlocked a great secret of the universe. It would mean that life could form under an enormous variety of circumstances. We'd know that there are many, 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 many more examples lurking at the edge of knowledge. We could envision countless other worlds. Then there's the other possibility. Earth continues to be the only life-filled planet in the universe that we know. That knowledge, though lonely, should endear our planet to humanity. It should inspire us to take better care of this precious and perhaps unique corner of the cosmos. It should let us see ourselves as Earthlings with fresh eyes, with a renewed sense of stewardship and purpose. Our planet is a laboratory to discover life beyond Earth and to rediscover ourselves. Thank you.